So this is second part of the discussion in real-time systems. The objective of this particular discussion is to understand the real-time system design and approaches. And as an obvious outcome in line with the objective is, you should be able to understand what are the different design aspects those are being there, and what are the different approaches those are being taken in order to design these real-time systems. So with this particular objective and outcome, let's quickly discuss on the recap that we discussed in the last part of the discussion of real-time systems. We typically understood what the real-time system is all about, in which we know that this particular real-time system is nothing but it's a classification or a part of embedded system whose output does not only depend on the logical correctness, but at a moment of time at which this output does occur. Means the timing of an application, meeting the timing of an application is equally important as of a logical functionality. This is what we got to know by the definition as well as a discussion of this particular real-time systems. As per the characteristics of real-time systems goes, we understand being a part of or being a classification of real-time systems, all the characteristics those are applied to embedded systems, those are equally applied to it. Like the system is a single function being an embedded one, it is being tightly constrained in terms of the resources. As well, it is reactive, that is the reaction time or response time has to be quick. As well, it's a real time itself, as the name itself is being indicated with it. So, and along with that, the major characteristic that it possesses is the system is deterministic and highly predicted. This is what the characteristics that this real-time system does have, as we have already discussed it in the last discussion. Okay, so maybe the types of the real-time systems, as we have seen for the hard real-time, soft real-time, along with the basis of what happens if the deadline are not getting missed, what is the resultant output even if the deadline is not being achieved. Means being missed a deadline, if the system can continue its operation with a degraded performance, we do call that as a soft real-time system, right? Or system incorporates with some kind of catastrophes where recovery of the system becomes highly impossible. So that kind of systems are referred to be as an hard real-time systems. Okay, so hard real-time, short real-time, then firm real-time, real real-time. All these are the sub-classification that we have seen in the last part of the discussion. Okay, we also saw a couple of examples of real-time system along with the real-life analogy example that we have seen last time, along with a few of the technical systems. Those can be categorized into the category of real-time systems. We also discussed about few of the misconceptions that many real-time system designers would have. These misconceptions were the part of the practices those are being followed in the past. And as people carried out those kind of aspects in the design, they found that these are the only methods by which the real-time systems are getting designed. But by advent or by virtue of the modern applications, those need some different dimensions to be used for design of real-time system. The so-called proven methodologies in the past, that and believing very firmly that these are the only methods, those create some kind of misconceptions and deviate the designer from being able to design effectively the real-time systems. This is what we have seen last time as an common misconception that designers would follow or designers would have with these real-time systems. Okay, now in the today's session, what I intend to discuss is what are the basic terminologies which are being used in the real-time systems. Now, being real-time systems is a time systems, as it's being expected, a timing analysis is at most important for this particular system, right? Timing analysis as well as the analysis by which the justification of underlying usage of the CPU, that has to be very well made of it. And that is what we'll discuss. Few of the terminology those are being used in common literature when the real-time system design is being used for it. Okay, at this particular point of time, let me tell you that there is a heavy mathematics involved into the design of these real-time systems. Okay, our treatment to this particular course is not so heavy mathematics. Okay, maybe whenever we are going to discuss an actual example, design example of real-time system, during which you would get to know that what kind of mathematics are being involved into it. Okay, now in order to understand the real-time system design, one need to understand what are the different tasks or events those are being there in real-time system, how exactly the events and systems are getting categorized, because real-time systems happens to be there as a very heterogeneous system. You cannot expect that most of the task would belongs to a same category of it. That is what I need to understand, the classification of the task or events, those would be used in the design of real-time systems, right? Then we'll see some sample model of real-time system where I cannot, as I said you earlier also, being a part of embedded system, being a category of embedded system, there are no preset rules for it. Whatever we are available, that is only the guidelines based on the experience of the designers. And with the guidelines, one would need to just go ahead or proceed in the path of design. Okay, so we'll see some sample model for real-time systems. Then we'll see what are the different approaches or the different considerations that one would need to go within real-time system design. And we'll discuss what are the different conclusions that I can draw with this particular session. Okay, fine. So let's first thing first, let's try and discuss basic terminology. Okay, so when I say that real-time systems are expected to be designed, then this design involves some of the terminology to be understood or being familiar with it. Okay, so being, as I told you, it's an analysis of the timing. So the first thing that I need to understand, that what do I mean by event and determinism? Okay, so I can see that whenever I'm defining any real-time system, or whenever I'm making an analysis of any real-time system, then I get to know there would be n number of activities those would be happening into it. Okay, some of the activities would happens to be an internal activity, some of the activities would be there as an external activity. Okay, so when I'm saying the execution flow of these real-time systems, the internal activities, those would keep on driving the flow of control. Okay, here the word of flow of control, that becomes very interesting and very important also, because whenever I am expecting the design to flow from input to output, I have some certain set of inputs based on some logic, based on some scheduling, based on some assumptions. I need to get that to be driven at an output. So it's a journey from input to output. So during that journey, I understand that there happens to be the flow of control. What do you mean by flow of control? The way in which I want the entire application to proceed from input to output, that happens to be as a flow of control. And as I always say to you, that in this particular real-time system, it is an important activity that the designer should establish the control over this flow of execution, isn't it? And flow of execution or flow of control, that has to be there in well control of this particular designer or developer. Okay, so as I was telling you, that some of the activities would be an internal activities, some of the activities are being there as an external activities. Okay, so internal activities or internal task, I can get referred those to be as in jobs. Okay, the terminology that I can understand, the internal activities I can get referred that as in jobs, and any activity that is being imposed from the external side, which change the flow of control, which change the flow of execution, that is referred to be as an event. Okay, otherwise jobs and events can be referred interchangeably. Okay, only the difference that happens is jobs with an external imposition, that becomes an events. And as we know that most of the embedded systems, even real-time systems, are interrupt driven systems. So whenever the flow of execution is getting deviated, or in the execution flow, the control is being established or control is being deviated because of the external activities that keeps on changing the flow of execution, then that particular events or that particular activities, I'm referring that as an event. And what your internal activity that keeps on happening, just like as an I have the flow of control statements are always being there as a branch statement. Okay, with the branch statement, what I get to know, the flow of control is changed, but still that happens to be a very internal to an execution of the program. So that becomes the basic task which are internal to an execution, and that is referred to as in jobs. Okay, that's what I said. We are interchangeably using jobs and events. Only the difference is that jobs with an external imposition, I'm referring that to be as an events for it. Okay, and as per the determinism is concerned, that I always told you that any real-time system, first of all, getting executed on the paper before getting it deployed. And that is what the determinism means all about. For every set of inputs, what would be the next state of output depending on the present state of output? This is what, if that is being known a priori, then I can refer my system to be as an deterministic system or highly predicted system. If you happens to get know with the term called as an FSM, finite state machines, where we understand the output state of that particular machine either depends on the input condition at that moment and output condition at that moment, okay, or the input condition and the previous input condition and output condition at that moment. And based on that, we even have got the categorization of the Mealy and Murray state machines for it, isn't it? So state machines are the perfect example of how the system can be made into deterministic, how the system can be referred to be as a deterministic. Because in state machines, we have the predicted output, we have estimated output for every set of input, which is in relation to a current output or maybe a previous output, isn't it? So that particular deviation or that particular derivation of the output state is highly deterministic. And that is what FSM is referred to be as a most accurate way of deploying the system in real time. But as we know, as the complexity of the system, by virtue of increase in the input variable, that goes on very high when we go with an FSM techniques. That is what this FSM technique, though, is a very foolproof system for the determinism, that cannot be used for the applications which really has got more number of inputs for it. Okay, so that is the reason, like we really don't follow FSM techniques for the real-time system design. If the real-time system design happens to be with a very small amounts of input and small amount of output, then definitely I can map the input and output with the help of K-map. I can design the sequential or sequential and combinational logic for it to attain that input to output relationship. Okay, but as the number of inputs keeps on increasing, that becomes very tedious and that becomes very cumbersome for designer to go with it. Fine. So we understood what is the job, what is the event, and what is determinism actually referred into the real-time systems. Okay. Then we'll see some of the terminology that is being used in the literature. The first terminology that let's refer that as a release time, RI. Now, whenever job or whenever any event is ready to execute with all its resources grabbed. Okay, please mark my words. Whenever any job or event is ready to execute from underlying processor with all its necessary resources grabbed, the time at which this particular job would start executing from the CPU, that is referred to be as a release time of that particular job. Means the instant at which the job actually or event actually getting executed from the underlying CPU, that instance is referred to be as a release time of that particular process or release time of that particular job or event. Okay. Many times in the actual systems, this particular release time, rather than having a number, rather than having a numerical, it is always being there in a range. Let's say that range happens to be RI negative to RI positive. So within this particular span of it, that particular task might get released for its execution. And that is what I refer to as an execution time. And when I'm not knowing exactly the time between the window of RI minus to RI plus, I refer that particular timing as to be as an jitter timings. And that's what it is being written, that release time in most of the cases or in many of the cases, it may be jittery. That means you might not get a single instance of the release time, but that release time is getting bounded by the actual frame of time, actual band of time. And that particular band of time, as we defined, is an R minus R plus. It depends on what kind of activities that it needs to do. Isn't it? Means some kind of leverage of that release time is expected into the system. Isn't it? As we go ahead, we'll get to know that getting exact design of real-time system is not that as easy as it might looks at this particular moment. Okay, we'll see. But I hope that this release time is being understood, is a moment of time at which this particular job would get executed from the CPU, whence every resource is being grabbed by it. Okay, then absolute deadlines. That means absolute deadlines are referred to be as and timings where a deadline of a task within which the task has to finish off its execution. There is no relaxations in the timing of execution is being given for it. Okay, as against of that, the relative deadlines that says to be that there happens to be some kind of relaxation that is being given in accordance with, in tandem with the task which is dependent onto the task which is getting executed for it. I mean, the word itself, relative deadlines, is quite easy, might be easy to understand at the moment. That as like I have got as I have got the very stringent deadline that I referred, absolute deadline within which task has to execute. If that is getting executed in isolation, if that task is getting executed in dependency of the other task, then the way in which earlier dependent task might be exhibiting the timing relations, according to that, the deadlines of this particular task might deviate. And that particular deviated deadlines in the range that is referred to be as an relative deadlines of it. Okay. The next, laxity type. Laxity type is what? Nothing but it's a type of real-time system. Okay. What is the degree with which the loss of not meeting the deadline is being referred of, like hard real-time system and soft real-time system. That is what referred to be as a laxity type of this particular laxity type into this real-time system. Okay. Then execution time, as it is being said, like what is the amount of time which is required for execution of a task. Once the task has got a release time, task also has got an end time. The release time and the end time of that particular task is referred to as an execution time of the task. And very important aspect that is expected to be known is referred as in CPU utilization. So let's see CPU utilization. This particular CPU utilization happens to be a very critical measure of real-time system performance. Why is it so? Because I have n number of tasks which are actually getting designed or which are actually getting executed from the underlying hardware, isn't it? So in case of a single processor system, what do I expect? I expect that the idle time for which the processor spend the idle time, that has to be minimized by anyhow, that has to be minimized to the maximum possible limit of it. That means my scheduling algorithm should be in such a way that it should keep on engage the CPU all the time. And that is what we refer to be as an utilization time of this particular CPU utilization has to be referred as a very critical measure of it. If the underlying scheduling algorithm is not so effective in order to get CPU utilized all the time for making some activities, specifically the foreground activities, specifically the activities which are designed by an application programmer. There also happens to be in different activities, as we know, right? Like for example, there might be some background activities, as we say, to be as in housekeeping activities. So these housekeeping activities, as this does not really much contributes into the actual functioning of the system under design. Okay, so that is what, rather than spending more time onto the housekeeping activity, the CPU should utilize its time for driving the foreground activity, driving the mainline activity of an applications. And in order to do that, the scheduling algorithm has to be adopted, which is very apt or which is very correct scheduling algorithm is expected to be adopted for it. And that is what, as this becomes a very critical or the major factor in the design, even in the last part, what your misconception that we have seen, that this is because of this particular part being so critical aspect of the system design, people tend to think that the scheduling mechanism policy or scheduling mechanism design is nothing but design of real-time system. No doubt this is important aspect of it, but this is not the aspect as we discussed in the last session also. Okay, but anyway, this is going to be a very interesting and important aspect for it, because the measure of the system or the measurable performance metrics of the system, real-time system, is one of the important measurable performance metrics is the CPU utilization of it. Okay, so let's say that it's How do I define this CPU utilization? Or the second name that is being given, time loading factor. Now this particular time loading factor, U, is a measure of percentage of non-idle processing. That's what I told you. When it is going for an some kind of clock ticking activity, some kind of housekeeping activity, so those are idle with reference to an application task. I'm designing an application not to make use of CPU for an underlying activities. Whatever bare minimum necessary, that will be explored. But most of the time, CPU should be utilized in the foreground, or the activities, those are being defined and designed by designed by this developer of real-time systems. Okay, so user task is at most important at this particular moment to execute from CPU. And the percentage of this time which CPU utilizes for the user's task is referred to be as an utilization, and that is what this non-idle processing terms that comes into the picture. Getting it? So this utilization factor for this utilization factor of task I, if I refer that as an UI, where for the task execution time EI, okay, that is referred to be as the task, this utilization factor of time of this task I, being having a specification of the execution time as an EI over the period of that execution frequency, or over the period of that particular execution, that is out of total time of execution. Okay, so that is being referred to be as a CPU utilization factor of this particular time for this particular task I. Now with this particular notion, if I have got n number of tasks in my system, then accumulation of the CPU utilization time of that particular individual task within that n number of tasks happens to be the overall system utilization time of it. And this overall system utilization time is given as the summation of I over 1 to n of this particular individual utilization time. And this individual utilization time, as it is being given by EI divided by PI, which is individual execution time of that particular task I over this particular period of that particular task I. Isn't it? Now, what do we get to know from this? From this equation, it is understood that if, for example, Pi happens to be, for example, 10 microseconds, okay, 10 microsecond, and if the execution time of that particular task for the defined period of the execution as in 10 microsecond, if execution time also happens to be a 10 microsecond, what does it indicate? It's a 10 microsecond divided by 10 microsecond, it's a 100% utilization. But will that be ever be the case? Because we understand the underlying scheduling, underlying policy of this real-time system happens to be a preemptive most of the time in nature. And that is what this particular task, which has got a period of this 10 microsecond, might not be available from CPU to execute that particular task. In between that, some interruption might happen. In between that, some new tasks are expected to be executed, depending on the policies of scheduling, depending on the occurrences of the event that those are being there for the system. And that is what we say, that whatever the execution time and the period of that execution, if that matches, it becomes 100% utilization. Okay, but the actual practical systems, when you are designing the real-time system, that never be the case for it. Otherwise, that becomes completely a non-preemptive system. And you might lose the response for the other tasks which are being deferred or delayed in the grade of having this 100% utilization. Getting it? So it's always a trade-off. Like many tasks are expected to be executed in tandem, but at the same time, the CPU utilization or the timing parameters of all those tasks also should be met with it. And that is the reason, as I said you, this becomes a very critical measure of real-time system performance. Getting it? So when we go with an design equations, or when we go with an actual designs of it, then definitely you would really appreciate how the importance of the CPU utilization is all about. Okay. Now, depending on the CPU utilization that I might have for this, you can say that this application-wise recommendation of the CPU utilization while designing. So CPU utilization can be targeted. Okay. So for if your application happens to be very simple applications or some various applications, if your utilization time happens to be 0 to 25%, then significant excess processing power of CPU may be more powerful than what is being necessary. So these applications are referred to be as a very simple applications where you don't need more than 25% of utilization of the CPU. Likewise, when you have got 26 to 50% utilization of CPU, they are said to be safe in the real-time domain. Means there is no fear that you would miss the deadline of it. See, I'm now trying to match up, I'm trying to correlate with the two factors. What are these two factors? Whether the safe zone is there, whether the critical zone is there. For what? For execution, for meeting the deadlines. Getting it? So if you get to know that the utilization factor happens to be 26 to 50%, there are valid reasons to believe that your system would be securely or very safely executing the deadlines which you have been actually planning for to design. Okay. And when it is being there in 51 to 68, then it is said to be even safer. Okay. And you can see that in between that, the factor of safety always maintained to be as in 2. And whenever factor of safety happens to be 2, we can be rest assured about the performance of that particular system. Is it not a general notion that we understood in the engineering philosophy? If that is the case, okay, if that is the case, then we understand that till 50% it's very safe, till 70% it is safe, no doubt. But after or when you go cross the threshold around 69%, then it becomes the theoretical limit. And this theoretical limit, the meaning of it is you definitely would need to strive in order to achieve this. In order to achieve into the practical sense, you need to make some extra efforts. You need to make some extra logic algorithms to be applied in order to design it. This is what it means for it. Okay. And when 70 to 82, it becomes challenging. It is referred to as questionable, but I would refer this to be as an challenging one. Okay. So this becomes the challenging, and most of the embedded systems, as per as the or real-time systems, as per as the this particular CPU utilization factor is concerned, the target, what did I say? The target that is to be set to be is around 70% of the utilization of CPU for the applications those you are running onto it. Because 30% time can be leveraged to be as the housekeeping or some other time that is to be executed for it. Okay, so 70% more than till 82%, it becomes a challenging one. After 83 to 99, it's not like you cannot design. You design it, but it becomes dangerous. It becomes all the time like it becomes a potential threat that the deadlines might not be met because CPU would be overloaded towards it is going towards an overloaded. Okay, and 100%, I mean 100% plus that you can design on it on paper, but in actual system that will not be there. Okay, that is what it's said to be a highly stressed system. So as per the embedded systems are concerned, 69 to 99, this is what and target that is being set for an CPU utilization during an applications. Getting it? Fine. So if this is being understood, you might also understood the, I mean, how it becomes very significant and critical system performance aspect. Okay, and this happens to be one of the very tangible, I would say, this happens to be a very tangible measure of the system's performance. Then let's discuss about what kind of events or tasks that real-time system might come across. And here you would get to know the scope of design of real-time system. Getting it? Scope of design of real-time systems can be understood by understanding the different classifications among the tasks and events. Now, what would be the basis of this particular classification? The basis of the classification is the event's occurrence time as well as periodicity of the occurrence of that event. Now, at this particular point, it fetches some little discussion to made out of it. Okay, so when I'm saying an application specific system as an embedded system, when I'm saying that embedded system to be executed within some timing, stringent timings, it becomes real-time systems. Okay, so in doing so, we also understood that most of the events happens to be an external events. Most of the events would change the flow of execution even with an internal events as well as external events. External events we understood in the name of interrupts, right? So when we have so many tasks which might be an internal or external, depending on the arrival time, depending on the occurrence time of this particular event, or by what period, by what frequency this particular events would keep on occurring, that happens to be a basis of classification of this particular task or event, isn't it? So some events might occur very periodically and at a regular interval, very periodically and at a fixed time of occurrence. Or some event might be estimated in time for their occurrence, but this estimation happens to be there within a band, not at a specific instance. Getting my point? And that is what, in general categorization, if we see, it happens to be initially goes with the first very initial thought of the general categorization as the synchronous event and asynchronous event. Getting my point? Synchronous event and asynchronous event. What does synchronous event would mean? The synchronous event would mean that these events has got some a priori known arrival time of it. That is what we refer to be as in this, depending on the arrival time, we refer that to be as a synchronous event. Like for example, when you are driving an activity with the help of clock, when you are driving an activity with the help of clock, we might claim that this activity refers to be as a synchronous one. Please mark my words. We might tend to refer that as a synchronous one because it is getting driven by the clock. Okay. But in fact, in practical sense, if you refer, then this clock always has got some skews, clock always getting drifted in actual practical systems. And that is what, even though the applications or the tasks which are getting driven or interrupts which are getting driven by the clock also, those are not being referred to be as a synchronous one, because they will not be having an exact estimate, but they would be having an estimate within the window. Depending on the latency of that, they would be defining into the window. And that is what they are referred to as an asynchronous event. Okay. So depending on the periodicity of arrival of it, I might define this into the two ways. How? The first task which keeps on repeating by its regular interval, fixed interval, that called as a periodic, or the interval is not being fixed. Okay, but it is expected it is going to arrive. Chances that it is going to arrive are maximum. That is what we said to be as an aperiodic. Okay, and sporadic is they are neither interval nor periodic. They are not with a regular interval nor they are periodic one. That said to be as an sporadic task of it. So if you refer this particular matrix as it is being said to be as a synchronous or asynchronous, again within these two events, I can have the category based on that particular periodicity. This classification is based on occurrence time, and this classification is based on the periodicity. Okay, so in synchronous, periodic, aperiodic, and sporadic, let's try and understand the cyclic codes, which are basically process scheduled by the internal clock. This is very interesting. A process scheduled by internal clock are referred to be as a synchronous periodic activity. Synchronous aperiodic activity is something typical branch instruction. Why it is typical branch instruction? Because you never know. That is certainly going to happen. But at what point of time this branching would be happen, that is not being certain for it. Isn't it? Branch would happen, but at what point of time it will happen, that is not being known. So there is no regular interval for arrival of it. Okay. But being this there as an synchronous one, synchronous aperiodic happens to be as a typical branch instruction. Okay. As well, the garbage collection is one of the examples that is being given. This garbage collection is a software which is being run basically when the fragmentation problem occurs for the memory. Whatever the garbage memory spots, or that we call fragments in the memory because of the virtual memory manager, swap in, swap out, that particular process, whatever is being there, that particular spots or that particular patches of the memory, to make it significantly used, they are expected to be logically linked in some other way. And that particular linkage software, that is referred to as a garbage collection. Okay. But this activity is definitely supposed to happen. That sort, it is going to be a synchronous one. But at what point of time it would happen, never knows of it. Okay. But the probability of occurrence of that particular task is less. Okay, as compared with the periodic one. The third task, which happens to be very interesting, that is called sporadic task. That is the branch instruction, for example, an error recovery. Okay, like for example, you are you are running an application, and let's say in application, you come across the situation where the denominator happens to be a 0, 1. And we know that dividing by 0 is not allowed in any of the case because it results into an infinite. And how do you store the infinite result as an infinite? There is no mechanism for it. That's what it is referred to be as a fault. It is referred to be as a system fault, and that we call to be as a trap. that we referred as a divide by zero error. And that is being mapped to be as an software exception to the system. Now, can you really estimate at what point of time this particular task would really pop up? This would pop up, but that is not being defined at all. That is what the percentage of or the probability of occurring this particular task, that is very, very minute. That is very, very less of it. That is what we define that task to be as an sporadic one. Okay. In asynchronous one, you can say that in asynchronous periodic, what I have, the clock generated interrupts. As I said, even though it is being clock generated, see, in synchronous periodic, I have the process schedule internally. Okay. But in external clock, like clock generated interrupts, as clock might be fear of getting it drift. Okay. Clock, because this is not completely with an internal, it's a clock generated only. Okay, internal clocks are said to be an atomic clock. Okay, the clock that you are using here with an asynchronous events, that has got a fear of getting it drifted. That is what, though it is being periodic one, it is referred to be as an asynchronous, where you don't have a regular interval of arrival. You have got this band of arrival of that interval. Okay, and if that particular band of arrival of interval happens to be regular, okay, then it's said to be as an irregular, that's said to be as an aperiodic. Okay, so in the next category of asynchronous and aperiodic, what do we have? This particular regular but not fixed period interrupt. That's what I was talking about. Aperiodic in a sense, like the probability of occurrence of that is less as against of this periodic task. And again, in the asynchronous sporadic one, what you have, externally generated exceptions, and those are referred to be as an random events. And when I'm saying it's a random events, any random process is always modeled with the theory of probability, isn't it? So that is what theory of probability would come to rescue when you have got the task which is of the order of sporadic and asynchronous one. Getting my point? So when we have known with this particular, sorry, when we are known with this particular categorization of the task or event, can you believe that your system would only have some kind of task in a single category? I don't think. This particular task, or for actual practical real-time systems, you might come up with the mix or the heterogeneous nature of the task. Few tasks would be coming into the category of synchronous or asynchronous, maybe periodic. I mean, depending on the application requirement, this task could pop up. And in order to give justification of execution time of application comprising of such heterogeneous scenario of existence of this task, which keeps on coming with different occurrences with a different periodicity, that really becomes the challenge of real-time system design. Getting my point? And that is what it is being popped up as a major field into a computer engineering. This is not just as a schedulable theory. This is not just based on the scheduling theory. It has got certain aspects to be even thought of. What are these different aspects? Let's go quickly for this. Okay. Or before that, if I just want to model the real-time system, then this real-time system, as you can see, that the scheduling and the resource access control and all, you can see that this is what referred to be as an task control graph, or it's called as task graphs. Okay. Maybe from input to output, in order to migrate the output, or in order to make a journey from input to output, you might have the task to be triggered in some other way, right? So for example, this task goes on this, like this would again go with this task, and this task means there would be one-to-one, one-to-many, many-to-one. That kind of triggering mapping would exist into the task graphs. So task graphs are expected to be designed at the very early stage of it. Okay, so after finding out the dependency and resolving dependency among the tasks to progress from input to output by this task graph, along with the task graph, what I can have is I may have one process, I may have the different processes. Depending on the complexity of an application, I might need to select on it. Okay, that's what at the today's moment, it becomes very essential by virtue of having a multi-core architecture available for a CPU. By virtue of having multi-core architecture available for the CPU, utilization of this multiple core in order to satisfy the higher requirements of CPU utilization, that is what the current trend in real-time system design. The days are gone where people only need to think as a niche area of real-time system design on a uniprocessor system. Now, by virtue of this particular multi-core architectures, exploration of multi-core architecture towards meeting the requirement of timing of real-time system, that is what getting sense at the moment as per the today's context of real-time systems are concerned. Okay, and that is what we always talked of any algorithm when they are getting a chance for the deployment, maybe AI, ML, compute intensive, control intensive algorithms. So every algorithm, when they are expected to match with the time deadline, the real multi-core architectures like NVIDIA's boards are there, which is basically GPU boards are there, or by virtue of Intel's multi-core architecture explorations with the Intel libraries that is being given as an OpenMP or MPI libraries. So these are all the aspects, those are expected to be underlined, considered for this. Okay, so after task graph, it becomes the processor, and then how does this particular resources are to be used in order to start or in order to get the control over the execution of the task. Means out of this n number of tasks, I really wanted to establish the control on execution of every individual task of it. And that individual task is again dependent on the different factors, right? And these different factors happens to be like this, for example, the amount of processors, those are being used, the different resources, those are expected to be used, and meeting of all these requirements in tandem with each other. Meeting of all the requirements in tandem with each others becomes the model of this real-time systems. That is what, there is no unique model as such is being given for the real-time system model. Okay, and this is what to be understood to be as a higher abstract level as a model of real-time system. Fine. Okay. Let's go very quickly. I'm not just spending more time onto it. Just go very quickly onto real-time system design approach and considerations that one would need to make out of it. Okay. Let's say that selection of the hardware and software, that becomes very interesting. Evaluation of the trade-off for the cost-effective solution that has to be thought in design of real-time systems, as well as it needs to deal with the different distributed computing systems, and the issues of parallelism and synchronization has to be dealt with it, isn't it? So that also happens to be one of the consideration. The second consideration is one should be very clear on the specification and design of real-time system and correct representation of the temporal behavior. The temporal is the word that is being related with ability to migrate with the time, with respect to time axis. How does the changes would keep on happening? So that particular representation, that means at every instant of time, I should be able to know what is the state of system. That is an ideal requirement that happens with this particular real-time system. Okay, so that consideration also happens to be there with it. Then understanding, this is something which is I would say neglected activity, but this is important one. Okay, understanding the nuances of programming language and the real-time implication resulting from their translation into machine code. That means the development tool's ability to give the predicted amount of time for conversion or translation into machine code also happens to be one of the factors. This is so because whatever we are discussing at the moment or discussed so far at the moment, we had only one assumption that the task priorities are getting statically defined. There is another category where the task priorities are expected to be scheduled dynamically also. So during that time, you might need to go with the in-application programming kind of activity. And during that in-application programming kind of activity, the development tools even would come into the picture in order to give you a certain amount of predetermined machine translation time into the machine code. So that is neglected one, but that also one of the consideration that happens to be. Then maximizing of system fault tolerance and reliability through careful design. This is obviously, as we know, fault tolerant systems are the systems which, in spite of occurring of some of the faults, system would able to tolerate that faults and go ahead for its further progressions. Okay, along with the fault tolerance and reliability, these are the consideration that we have seen even during the characteristics of real-time systems also, right? The design and administration of test and the selection of test of the development equipment, that also becomes a very interesting consideration for real-time system. Okay, then taking advantage of open system technology and interoperability, that also becomes one of the consideration. Let me brief this very quickly. Like, because of the open-ended or open system operating system, even in that case Linux and all that, so when we have this independent abilities, independent IP properties are getting developed because of this open-ended system. There has to be some migration rules. There has to be some rules by which the interoperability from one system to other system is expected to be guaranteed. Okay, and this particular interoperability in the open-end system becomes an issue or becomes a design consideration and approach for it. And in order to meet this interoperability, you might be aware that Linux has got one standard that's called an POSIX, Portable Operating System Thread Interchange Standard. Okay, so that kind of standards are getting developed in order to address the interoperabilities only because of the open system connect. Or then again, measuring and predicting response time, reducing it, that becomes the consideration. Performing the schedulability test, that is determining and guaranteeing deadline satisfaction a priori, is the focus of most of the scheduling theories. I mean, these are what the consideration that one would need to understand it very meticulously. Okay, and the list goes on. As I said, these are only the guidelines. This particular list of the considerations or the approaches would keep on popping up as per the expertise, as per the experience that keeps on developing or keeps on coming out onto this particular real-time system design. Okay, quickly we'll go through the conclusion, which is very interesting conclusion I want to draw out of it. Okay, and that conclusion happens to be the real-time systems are the complex sub-discipline of computer system engineering that is strongly influenced by. Now let us understand what are the factors those are being influencing this real-time system design. Okay, so if this is what real-time system design that we see, then the different factors that would contribute or basically influence are control theory that has to be very true and very fairly understood. Then maybe programming languages are known to be very good. Then operation research in the form of scheduling theory that is to be very high, tall order proposition. Then the algorithms, parallel algorithms, all this kind of things are being there. Then queuing theory is expected to be there in order to make this particular sporadic and a periodic task to be scheduled one. Then operating system ability to give the constant known a priori service time in order to meet the deadline, that also becomes a very interesting part. And this is what we are discussing the real-time operating system all about. Then maybe software engineering aspects, all the different different prototypings or different SDLC cycles and all, that also becomes to be a very interesting aspect of software engineering towards real-time system. Then I might have computer architecture, as I said, you multi-core, many-core, maybe some or architectures with elevated branch prediction kind of techniques and all these particular modern computer architectures also contributes and influence into design and development of real-time systems, and the different data structures that I'm designing or that I'm using for development of my applications. Now, if you see all these particular factors, what is being left out to discuss now? Means, can this be only thought to be as a narrow channel of the real-time system design? Almost everything is being required. That is what embedded systems as such is not really as a subject or course, but rather it becomes the field, or rather it becomes the art of deployment. And that is what we need to understand here as a conclusion of this particular discussion, that along with logical correctness, when I need to build up the time constraint execution on my embedded systems, then I might need to go with all these kind of aspects to be there. That's what it becomes very challenging. And that's what it becomes a very niche area at the moment in design and development of embedded system as a part of real-time system design. Okay, that's all from my side for this particular today's talk session. Instructions, as I said you, most of the literature is being there from this real-time system design and analysis by Philips Laplante. The second part is like, as I said you, real-time systems by Jane Liu. And next time we are going to discuss about the design software considerations of this real-time systems. Okay, I thank you for joining this particular session.